The next part we're going to look at is sort of an exploration of symmetry and what to expect with certain types of functions. So the thing that we're going to discuss here is even and odd functions. So I'm going to switch over to Desmos for a second, and I'm going to graph a whole bunch of odd functions, and you're going to see if you can tell me something you notice. So my first odd function would be my linear function, y equals x. My next odd function would be y equals x cubed. My next odd function would be y equals x to the 5. And then lastly, let's just go up to y equals x to the 7. Is there anything that you notice about these three graphs in terms of their symmetry? Hopefully, you're thinking from the last lesson that these four graphs are symmetric about the origin, meaning that if you look at this gray point here that they all share at 1, 1, it also has a point down here at -1, -1. In fact, all odd base functions, if I went x to the 9, x to the 11, and so on, they all demonstrate origin symmetry. Even if I put a negative in front of them, right? It's still origin symmetry, just in the other way, right? Now you can see you have a point -1, 1, and you'd have a point 1, -1. So one of the things that we use to describe an odd function is potentially its ability to have symmetry across the origin. Now, one thing I always like to point out is that not every odd graph has symmetry about the origin. So for example, if I graphed a linear graph like x plus 5, this graph is odd, but it's no longer symmetric about the x-axis or the origin. And that's okay. It's still an odd function, but you couldn't determine that this was an odd function based on symmetry. So what we're going to be doing in this lesson today is looking at, can you tell from an equation whether something is an even or an odd function based on its symmetry? So the first thing we're noticing here is that odd graphs are symmetric with respect to the origin, but not every one is. Okay, but all of our base ones is. So one of the tests for an odd function is whether it's symmetric about the origin. The second one we're going to look at is what about all of your even graphs? And so if we go back here, and all we do is we change these to even functions, so something like x squared, right? Or x to the 4. Doesn't matter whether I put it positive or not, and we'll just show these graphs again. And we go x to the 6, and lastly, let's just do an x to the 8. Anything you notice about these even graphs? Well, hopefully you're recognizing that they're all symmetric about the y-axis, meaning if you have a point here at -1, 1, you'll also have a point here at 1, 1. To be symmetric about the y-axis, you have an x and a negative x value that gives you the same y value. And so one of the tests for whether something is an even function is whether it is symmetric about the y-axis. Now, you could also say that a graph is neither symmetric with respect to the y-axis of the origin, and then you can just say that it's neither even or odd. But I will make a little caveat that you can be odd and still not be symmetric about the origin. You can be even and still not be symmetric about the y-axis, and that's okay. You can still be even or odd, but not when you're testing for it. The last thing here, I just put a little question for you. We've covered origin symmetry and y-axis symmetry. Why can a function not be symmetric about the x-axis? Well, I just drew a graph that's symmetric about the x-axis, and what do you notice? Well, it fails the vertical line test, so it's not a function. So no functions will be symmetric about the x-axis. So what we're going to do here is we're going to look at 4 equations of functions and determine whether they are even, odd, or neither. And we're going to do that by testing it algebraically. Now, when I look at an equation like this, I'm going to tell you this is an odd function. It is. This is an odd function because the highest exponent is 3. And when we do chapter 4, we are going to call this an odd function. But in chapter 2, we're going to say odd, question mark, and we're going to test whether it has origin symmetry. To test for origin symmetry, we plug in x for negative x, or negative x for x, and we plug in negative y for y. So into this original function, we're going to plug in negative y for y and a negative x for x. And we're going to test it. So we're going to have negative y equals, this will come out negative, so this will be negative 2x cubed. This will be positive 4x. But then to get y by itself, we're going to divide everything by negative 1. And we'd end up with y is equal to 2x cubed minus 4x. So since this equation and this equation match, we are going to say that this function is odd. Now the nice thing about this is that if it's odd, you don't have to test if it's even. And so that's why I always, first of all, look at the highest exponent on x, and if it's odd, I'll test if it's odd, and I'll never actually test if it's even because it can't be, but I definitely narrow it down. So if it comes out as symmetric about the origin, you can say that it's odd. If it came out that it was not symmetric about the origin, you would say it's neither even nor odd in terms of its symmetry. But it can still be odd. It just bothers me a little bit. Can you tell? The other way is I gave you this picture so you could tell from this one that it has origin symmetry, because if we picked a point here like negative 1, 2, then there should be a point somewhere over here at 1, negative 2. And look, there is. So this guy definitely had origin symmetry, and we tested that algebraically. Here's another function. So again, should I test whether this function is even or odd? Well, because the highest exponent on x is a 3, I'm going to test whether it's odd. Now you can test if it's even as well, but I can tell you for sure that it will fail. An odd function can never, ever test as even. So we just take that out of it. So I'm just going to say odd, question mark. And to test whether it is odd, we're going to look for origin symmetry again. So we're going to replace y with negative y, and we're going to replace all the x's with negative x's. I'm going to run out of room here. Good, and then let's multiply through, so I get negative y equals, this will stay negative. This will be a positive times a negative, so this will be negative. Negative times a negative is a positive, and then plus 4. And then lastly, I'm going to divide everything by negative 1, so I end up with 2x cubed plus 3x squared minus 4x minus 4. Since these functions do not match, this is neither odd nor even in terms of its symmetry. And again, I would never test if this one has y-axis symmetry. You can, but it will fail. And that's because an odd function can never have y-axis symmetry. So just cutting out a bit of your work is that if you look at what the highest exponent is and it's odd, don't test if it's even. If you do, great, but you don't have to. All right, 2 more. This one, I mean, I can see right away from the picture that this has y-axis symmetry, but we're going to double check. So the first thing we're going to check is that the highest exponent on x is even. So I'm going to say even question mark, and I'm going to test for y-axis symmetry. To do that, I'm going to replace x with negative x, and then I get y equals negative 3 times negative x squared plus 4, which the square is going to make that positive, so it's going to stay negative 3x squared plus 4, and since it matches, I will say that this guy is even in terms of its symmetry, and because the highest exponent is even. Then you get to a function like this, and I'm like, well, I don't know. Is this even? Is it odd? What's the highest exponent on x? And if you don't know, so this is why I asked this one, is because it's not so obvious. There's something other than, you know, a 1 or 2 or 3 or 4. Just test both. So let's test for odd symmetry as first. So we'll plug in negative y, and we'll plug in a negative x. So this is going to stay negative y. Absolute value makes anything positive, so this will just be the absolute value of x, and then minus x. And then divide everything by negative 1, we get negative the absolute value of x plus x, which does not match, so it is not odd. Then we test to see whether it's even, because this one I didn't know where to start, so you have to test for both. So to test for even symmetry, you're looking for y-axis symmetry, so you're replacing x with negative x. So again, negative absolute value of x plus negative x would give me the absolute value of x minus x, and it failed that one as well, so you would say that this is neither even nor odd. Awesome. All right, so that is the last part of these weird lessons about symmetry. And if you look at the textbook, they do it slightly different in how they write it, but the gist is the same. And I just like the consistency from the lesson on symmetry to the lesson on whether something is even or odd.